Hello and welcome back to CS 11747 Neural Networks for NLP. Today we're going to talk about language modeling, efficiency, and training tricks. So as I mentioned in the first class, language is hard, and one of the hard things that we can do with respect to language is deciding whether a particular sentence is grammatical or natural. So we have Jane went to the store, which is a perfectly natural English sentence. Store to Jane went the, which is kind of word salad and not grammatical at all. Jane went store, which is not grammatical in English due to the lack of determiners, but could be grammatical in other languages. Jane goed to the store, an incorrect conjugation. The store went to Jane, which is perfectly correct grammar-wise, but maybe a little bit strange semantically. And the food truck went to Jane. And what we want to talk about now is language modeling. And language modeling is essentially the tool that we can use to answer these questions about whether a sentence is particularly natural or probable. So we frame the idea of language modeling basically as calculating the probability of a sentence. So let's say we define our sentence as big X here. And the way we model this is we use the chain rule of probability, where basically we have large I words in the sentence. And at each point, we want to calculate the probability of the next word given the context. And because of the way probabilities work, this is actually a perfectly reasonable way to decompose the prediction problem for large X, and these two expressions are equivalent. So this is a very nice thing because basically now what we can do is we can do a prediction over the next word. But the difficulty is this is not an easy thing to do. Even if you ask a human to predict the next word in a sentence, they're very likely to not be able to predict it accurately. So the first thing I'd like to do is I'd like to review count-based language models. And because I think a lot of the people in this class will have taken an NLP class before, this might be review for some of you, but please bear with me because I think it's really important to make this connection. And in fact, what really convinced me that neural networks were the way forward for NLP was precisely understanding the connection between kind of a simpler model, like a count-based language model, and what neural networks can do for us. So a count-based language model basically is a model that tries to calculate the probability of the next word by calculating the frequencies of particular word sequences. And for example, the way this works is if we look at the top term over here, this is calculating the probability of the word xi based on the previous n-1 words. So for example, if we have the boy walked, the probability of walked would be calculated by counting the frequency of the boy walked and dividing it by the frequency of the boy, the previous context. However, this can have problems. So for example, if we have a somewhat rare context, like let's say we have a context like Mr. Biden understood that it was, or something like this. Even that is not an appropriately rare context. But let's say we had a somewhat rare context that we were looking at. If that was the case, this probability up, or this count up here might become 0. So essentially what count-based language models do is they calculate the probability of the next word given the current context, given a longer context, but fall back to shorter contexts. So when they don't have very much confidence in the context that they've seen so far, they fall back to a shorter context that they're more confident in and might be more frequent. And there are kind of complicated methods to do this based on statistics. I won't go into them here because that's not the point of this course. But for example, there's a method called modified Kneser-Ney smoothing that calculates the smoothing coefficients and probabilities appropriately to do a good job of predicting the probability of the next word. And I'd also like to talk about evaluation of language models. So how do we evaluate our systems, our language models based on how well they are predicting? And the standard way of doing this is to calculate the log likelihood of all the sentences in a corpus. So here I'm using the variable e to represent a sentence. I'm using this cursive e test to represent the test corpus. And we sum the log probabilities of all of the sentences in this test corpus here. So this is one way to calculate the how good a language model is doing, and the log likelihood of a relatively good language model will likely be higher than the log likelihood of a less good language model. And importantly, this is a test corpus, so this was not available to us at training time. So we're testing how well the model generalizes to new data. We can also do things like per word log likelihood. And the basic idea here is instead of calculating the likelihood of the whole corpus, we calculate the likelihood of the whole corpus divided by the number of words in the corpus. And the reason why this is useful is because it allows us to get roughly comparable measures of how well the language model is doing, even if our test set is larger or smaller than another test set. We can also calculate cross entropy, and essentially cross entropy, what it is it's the negative log probability divided by the number of words. And usually this log probability, or often this log probability, is expressed in base 2. And I won't go very much into the details here, but basically this has to do with an information theoretic measure of how many bits you would need to represent the corpus given this language model. And finally, we have a term perplexity. And what perplexity is essentially we take 2 to the entropy, and the perplexity has a interpretation as well, which is kind of the average branching factor of the number of words that you would have to pick before you got the correct next word. So let's say you had a language model and it guessed the next word randomly according to its probability distribution. If your perplexity was 10, then you would have to make approximately 10 guesses before you got the actual next word. So that kind of is intuitive, and it's pretty widely used in evaluation of language models. Okay, so that was a little bit of detail on how we tell whether language models are doing well. So what kind of things can we do with language models? So one thing that we can do is score sentences. And essentially, this will do exactly what I suggested that we be doing before, which is taking a sentence in and calculating how grammatical or natural the sentence itself is. So if our language model is doing well, it will look at this Jane went to the store and give it a high probability, store to Jane went and give it a low probability. So this can be useful for a number of things. For example, it could be used for spell checking, or it could be used for grammatical error correction or something like this. So if you, for example, open your favorite document processing software, it might give you little red squiggles for misspelled words or little blue squiggles for ungrammatical words. And language models can be used to essentially do this at much higher accuracy. Another thing that we can do is generate sentences. So what we do essentially is while we haven't chosen the end of sentence symbol, while the model hasn't decided that we've reached the end of the sentence, we'll calculate the probability of the next word and sample a new word from the probability distribution. And why is this interesting? This allows us to generate new text, or if, for example, we give the language model a prefix, human specified, the model can generate text conditioned on that prefix, which could allow you to, generate a story or something interesting like that. So I talked a little bit about count-based language models, where we basically add up the previous context and divide to calculate the probability of the next word. However, these have some problems. So one issue is that count-based language models, because they treat each word in the context completely differently, they cannot share strength among similar words. So if we had she bought a car, she bought a bicycle, and she purchased a car in our corpus, nonetheless, she purchased a bicycle, where purchased is very similar to bought and bicycle is very similar to car in terms of the contexts that they appear in. The simple count-based model would not be able to handle these and would not be able to predict bicycle with high probability in this context. As a solution, there are things like class-based language models where people tried to group words into classes and calculate the probabilities based on the counts of the classes. Another issue is that these models could not condition on context with intervening words. And as a solution to this, there were skip-gram language models, which basically skipped over particular words and calculated based on the words before the gap here. And they also cannot handle long-distance dependencies. So for example, if we have, for tennis class, he wanted to buy his own racket, and for programming class, he wanted to buy his own computer. This has a very long intervening context of about 7 words, and very few of these count-based language models could consider this long of an intervening context. So count-based models essentially had different solutions to this, things like cache models, trigger models, topic models, syntactic models, etc. And this was how they solved this issue. So there's actually a very interesting paper by Joshua Goodman called A Bit of Progress in Language Modeling, where in the 1990s, I believe, he went in and he tried to combine all of these models together to make the best model he possibly could. And this was a lot of work. It took him, a lot of effort to implement all of these things, combine them together in a nice way by smoothing together their probabilities, et cetera, et cetera. And at the time, I thought this was a very nice paper because it essentially described all of the things we needed to do to make these language models work as well as possible. However, the kind of epiphany that I had that caused me to be interested in neural networks for natural language processing is that a lot of our neural network models can handle all of these things very gracefully and elegantly in a single model without all of this engineering work that Joshua Goodman had to do back in the 1990s. So because of this, I would like to continue and discuss some models gradually moving towards neural language models and explain how they solve the problems that I've outlined here. So the first alternative I'd like to talk about is featurized log linear models. So what do I mean by this? Basically, these models, what they do is they calculate features of the context. And based on the features, they calculate probabilities. And they optimize the feature weights using gradient descent, like what I talked about in the previous class. So for an example, if we look at a context where the previous words are giving a, in a count-based language model, we would calculate all examples of giving a followed by another word and divide by the total frequency of giving a. However, in a feature-based model, we might have each of the words we're predicting, and instead of counting the contexts, we calculate features of these contexts. So the first feature we might have is a completely context agnostic feature called the bias, B, which we just add to the score of each word regardless of the context it appears in. So essentially what this is telling us is how likely is the word in the first place. A second feature we could calculate is, given the previous word, how likely is the particular word? So this is kind of like a count-based language model where we only look at the previous word. And in this particular case, because our context is giving and the, despite the fact that they are very common in general, they're very unlikely to follow giving because in English a determiner doesn't follow a determiner. So they would have a very low feature value given that the previous word was And then in addition, we might have a feature based on the fact that 2 words ago we saw the word giving. And in this particular case, we might upweight the values of talk or gift because these are things that tend to be given and thus are kind of appropriate for this context. So based on this, we take the scores for all of our features with respect to all of the words in our output vocabulary we'd like to predict and add them all together into a total score. So once we have scores over various options, we would like a way to convert these into probabilities because in neural network models or probabilistic models in general, we would like to have an idea of the probability of seeing a particular phenomenon. So the standard way to do this in neural networks is using a function called the softmax. And the way the softmax works is essentially we have a score over the thing that we would like to predict. And the score is calculated based on the context. So we then exponentiate the scores. So we take e to the score. And then we renormalize. So we take e to the score of a particular next word and we divide it by the sum of e to the score for all of the words in our vocabulary, all of the things that we would like to predict. So by doing so, we can take these kind of arbitrary scores and convert them into a probability vector that sums up to 1. So in our language model, we apply this softmax. Now let's look at this as a computation graph, like the ones we talked about in the previous class. So essentially the way this works is we have a lookup, and each vector that we look up is the size of the output vocabulary. We have another lookup. So these are 2 different lookup tables, essentially. The first one is for words 2 words previous. The second one is for words 1 word previous. We have our bias. We add all of these together, and we get our scores that we then feed into a softmax and get probabilities. So what does this look like? This looks a little bit like the bag of words model that we discussed in the first class that we use for text classification. The only difference being that the bag of words model was order invariant, so it used the same lookup table regardless of the order of the words, whereas here we're using a different lookup table based on the order of the words. So this is very simple. It's a way to calculate a language model, and one thing I'd like to point out, or we'll point out later, is the features that this has compared to a count-based language model. Before I do so, though, I'd like to talk about what I mean by lookup. So lookup essentially can be viewed as grabbing a single vector from a big matrix of word embeddings. And so let's say we have a big matrix where the width of the matrix is the number of words, and the height of the matrix is the size of the vector. So when we call lookup 2, this would be grabbing the second vector, or if it's 0 index, the third vector, and grabbing it from this big matrix. Another way we can look at this is we can look at this as multiplying by a one-hot vector. So in other words, we multiply by a vector of 0, 0, 1, 0, 0, and get the vector for the third row in this, or third column in this matrix. So the second way of viewing this is very nice. It's elegant mathematically, but it has a problem if you actually implement things this way, which is that a matrix multiply over a potentially very large lookup matrix could be very expensive if you did it naively. So in fact, most of the time when you do a lookup of word embeddings or something like this, you will use this top option of essentially grabbing the vector directly from memory without doing a multiplication. However, the second one is still useful to know. For example, let's say you wanted to look up 20 words at one time. It might be more computationally efficient to sum the counts of all of the words and multiply than it would be to look up each of them individually and then sum afterwards. Or alternatively, let's say you wanted to look up an embedding for a probability distribution, which we do in some of the more advanced learning algorithms. You could also do that by specifying this as a probability distribution here. Okay, so now let's talk about training a model. So remember, to train our models, we calculate a loss function measuring how bad our predictions are, and then change the parameters to reduce the loss. So the most common loss function for probabilistic models is the negative log likelihood. And essentially how we calculate this is by taking the softmax output and taking the negative log of this and grabbing the correct answer, looking up the correct answer in this matrix. So this is an extremely common operation. So, if you're using a neural network toolkit, then this will likely be implemented as a single thing, like a negative log likelihood loss, NL loss in PyTorch, for example. So with parameter update, backpropagation then allows us to calculate the derivative of the loss with respect to the parameters. And simple stochastic gradient descent optimizes parameters according to the following rule like this. So essentially, we have our derivative of the loss with respect to the parameters, and we subtract multiplied by the learning rate alpha and update the parameters to their new value. So this is a basic learning algorithm. The next thing that I'd like to talk about a little bit is choosing your vocabulary for how you learn this language model. So one thing that you should know is that you will need to deal with rare words in your corpus. And the reason why you will need to deal with rare words in your corpus is because language has a long-tailed distribution characterized by Zipf's law, where there are many, many words that are very, very infrequent. So no matter how large your corpus is going to be, you're always going to be encountering more words that you've never seen in your training data. So how do we deal with these unknown words? So as I said, we don't have all the words in the world in our training data. But on the other hand, there's an issue specifically with neural networks or other featurized models, that larger vocabularies require more memory and computation time. So for example, if we are predicting the softmax and we have a very, very large vocabulary, we will have to calculate the softmax over this very large vocabulary at every time step, and that can become basically ponderous. So a couple ways to do this are having some sort of frequency threshold. For example, removing words that only appear once in the corpus. Having some sort of rank threshold, taking the top most common 32,000 outputs. Or we're not going to cover this today, but you can also split the words in your corpus into smaller substrings and use them using a method like byte pair encoding or word pieces, which we'll talk about later. Okay, and when you're evaluating a language model, one important thing to know is that the vocabulary must be the same over the models you compare. Or more accurately, all models must be able to generate the test set. It's okay if they can generate more than the test set, but not less. So to take an example, let's say you have a vocabulary of 32,000 words, and you take every other word and you replace it with an unknown word symbol. If that's the case, then basically you're telling your model that it doesn't need to worry about generating these unknown words. However, if a character-based model was used to generate the words, then that would be a little bit unfair to the character-based model because the character-based model was being asked to generate even words that the word-based model had given up on by calling them an unknown word. So this is an important thing to know about if you're creating language models. Another issue that you should be familiar with is that if you are evaluating models based on different subword segmentations, like byte pair encoding or word pieces, then you need to make sure that you're dividing by the same number. So don't divide by the number of subwords if one subword segmentation has more subwords or fewer subwords. So this is a small but important point to know if you're evaluating language models. So we have a demo code here. I'm not going to walk through it in the video, but please feel free to take a look at this. It implements this log linear language model. And based on the featurized language model that I just talked about now, this can handle some of the problems that we talked about. So which ones of the problems that we talked about have been handled by introducing this kind of feature-based computation method? So the first one, we still haven't solved this problem. And the reason why we haven't solved this problem of sharing strength among similar words is because we're still calculating a one-to-one correspondence between each feature we're calculating and the word that we are predicting. So for example, if purchased appears to words previous and our expected output is bicycle, if we've never seen this combination together, we still won't be able to handle it or upweight it appropriately. One problem that we did fix was that we cannot condition on the context with intervening words. So we are able to handle this because, for example, if we looked 2 words previous and saw doctor, then we might know we'd have a very high probability of picking Smith here. And we had a feature that directly captured that in our log linear model. Another issue that we have not solved yet is long distance dependencies. So if you remember, our featurized model only looks 2 words previous, so it wouldn't be able to capture this correspondence here. Okay, so this was basically warm up, and now I'd like to move into the kind of core idea that we're handling in this class, which is to move beyond linear models. So linear models cannot learn feature combinations. So for example, if we have students take tests, this obviously has a high probability, correct? And teachers take tests has a low probability. And then we have students write tests has a low probability, whereas teachers write tests has a high probability. And based on this, what we can see is that none of the features that we introduced so far with our linear model are able to handle this. So if we look purely at whether students appears 2 words previous or teachers appears 2 words previous, we don't know if the probability of tests is high or low. And if we have take and write 1 word previous, again, we still don't know if the probability is high or low. So we really only know whether this probability is high or low based on multiple words in the past and their combination together. So what can we do? There's a couple things that we could do. We could remember combinations as features. So we could have individual scores for students take and teachers write, for example. However, the issue here is that we might have a feature space explosion. So we might have a very, very large number of these features, and we wouldn't be able to learn these robustly from the data that we have. It'd also be expensive to store. And so what we can do instead is we can use neural nets. So here's an example of a neural language model, which was introduced by Bengio et al. In 2004. And basically the way the model works is it looks up a word embedding for the word giving. It looks up another word embedding for the word a. And this gives us a large vector 2 times the size of our word embedding vectors that represents our context. We then take this vector and we run it through an affine transform and a nonlinearity such as a tan H to extract hidden features from this context. And as we discussed last time, the moment we start doing this sort of feature combination and nonlinearity, we now are able to express kind of arbitrary combinations of the input features. So this allows us to take giving or teachers take, students write as features in this hidden purple vector here. We then take these features, we multiply them by a weight, add a bias, and get scores. We can then take the softmax and get probabilities corresponding to these scores. So this is great. It allows us to calculate combination features in a very simple and efficient manner. It also allows us to share strength among words or contexts. So for the word embeddings, if we have similar input words, they can get similar vectors. So for example, if we have giving or, well, giving maybe isn't the best example, but like walking and running, for example, they would have very similar vectors, or and the might have very similar vectors. So even if we have a training example where we haven't seen that exact word, we can still share strength with other contexts that have similar words in them. In addition, similar output words get similar rows in the softmax matrix here. So if words are likely to occur in similar contexts, we can also share strength among them as well. And finally, similar contexts will get similar hidden states. So that means if we see contexts that tend to be followed by the same words, then they can also share strength among their training examples. So obviously this solves the first problem that we talked about. So now the model is able to share strength among similar words and even similar contexts. It's still able to condition on intervening words, or condition on context with intervening words, because we're feeding 2 words previous into the model just like we're feeding 1 word previous into the model. However, this is still not able to handle long distance dependencies, and we'll get to this problem a little later. And like the featurized language model example, we have an example for this as well. One important trick that we can use in these models is tying input and output embeddings. So we can share the parameters between the input and output, where basically our softmax matrix is an identical matrix to the word embedding lookup matrix. And this is very useful because it basically reduces the number of parameters we have in half, which has time and efficiency benefits. And it also is better from the point of view of learning, because both for every training example, we learn both the lookup matrix and the softmax at the same time in a similar way. So this is very effective and widely used. And if you want a challenge, you can try to implement this in the previous code that we made available to you. Okay, so now that we have the basics of neural language models, I'd like to go into some details about how we train these language models. And specifically, I'll first start out by talking a little bit about optimizers. So if you remember from the last class, standard stochastic gradient descent basically calculates a gradient of the loss function with respect to the parameters. And here I will call this GT. So this is the gradient of the loss. And then we will take our previous parameters, theta t minus 1, and subtract this gradient of the loss function, multiply by a learning rate, eta. And there are many, many other options. I'm going to go through a few of them here, but I've also added Rooter 2016, a blog explaining these in the reference. So please take a look at that if you'd like to know more. So SGD with momentum is our first option, and it makes a small change. And basically the idea is that it allows you to remember gradients from the past time steps. So we have our momentum term, Vt, and what we do is we take the previous momentum term, which has accumulated a lot of information from the previous gradients, multiply it by gamma, where gamma is usually a number between 0 and 1 and kind of degrades our momentum. And then we add in eta gt. And so what this is doing is then we add this term into our gradients, or subtract it from our gradient, from our parameters. And the basic idea here is in stochastic gradient descent, especially if we have a relatively small batch size or a relatively small number of examples contributing to the gradient, then this essentially will prevent it from swinging around widely every time we get a new example and maintaining course in approximately the same direction, stabilizing training. Another option is Adagrad, and Adagrad basically adaptively reduces the learning rate based on the accumulated variance of the gradients. So we have this big GT, and this is based on the variance of the gradient. So we have the gradient times the gradient, the squared current gradient. And then we take our regular gradient, we multiply it by eta, our learning rate, but then we divide it by this variance plus a small noise term, eta, which helps us prevent getting 0 in the denominator here. And the basic motivation behind this, which is particularly salient in NLP, is we might have some parameters that are updated frequently, and thus we're very confident in them, and we wouldn't like them to swing around widely based on individual gradient values. However, we have other parameters that we haven't seen very many gradient updates for, and these parameters we'd like to modify a larger amount. And within NLP, a very common example of this is, for example, particular word embeddings. So frequent word embeddings we'll see frequently, and we don't want to move them around a whole lot if we get a gradient for them. But word embeddings for infrequent words we may only see in a few examples in the entire training corpus. And thus these ones, when we do see them, we'll want to update them more to make sure they get learned properly. So that's the basic idea here. One problem with Adagrad, however, is that this gradient term GT gets larger and larger throughout training, which means the effective learning rate gets smaller and smaller for parameters that are updated frequently. And because of this, the learning rate can get very small and training can stall, and this has been fixed by using the rolling average and other techniques such as Ada Delta and RMS prob. And finally, I'd like to get to Atom, where Atom is the most widely used optimizer in most neural network learning algorithms today, and especially in NLP. And basically it considers both the rolling average of the gradient and the momentum. So we have the momentum term, MT, which we have here with beta 1 and 1 minus beta 2, and the gradient term, the variance term. And we also correct for bias early in training. So basically, we take the momentum and we divide by 1 minus beta 1 to the t, and essentially this allows us to gradually roll in training without taking big steps at the very beginning. And then our final update looks a little bit like this. So basically, it's very similar to the Adagrad update, except we are additionally adding the momentum term from SGD with momentum. So you can kind of think of Atom as the combination of SGD with momentum in Adagrad, combining their two advantages together. So next, I'd like to move on to training tricks. So some training tricks that we definitely should know, or everyone should know when they're training neural network models for NLP. Number one is shuffling the training data. So stochastic gradient methods update the parameters a little bit at a time. As you saw before, basically they're taking small steps through the parameter space for each training example or training mini batch. But what if you had some strange data ordering where I love this sentence so much, or some other extremely positive or extremely negative sentence happens at the end of training data 50 times, or many, many times. So basically this would cause us to overweight the things that we've seen later in training. And in order to do this, to train correctly, we randomly shuffle the order at each time step. Another issue that you need to deal with is overfitting. And overfitting basically means that you train and do well on your training set, but then you don't generalize to the test set because you've learned to fit the training examples, but you've learned to fit them too much, fitting onto spurious features that don't hold in the test set. So we have a number of ways of fixing this. The first way is early stopping. And basically what this does is monitor performance on a held out development set not included in the training data and stop training when it starts to get worse. So basically monitor for overfitting and stop training when you're done overfitting, when you start overfitting. Another one is learning rate decay. And this is essentially gradually reducing the learning rate as training continues, or reduce the learning rate every time the dev performance plateaus. So instead of early stopping, you can reduce the learning rate and continue training. Finally, if you're doing learning rate decay or early stopping based on dev set performance, you should be aware that training is unstable. So your dev set performance might get worse some of the time, and but on the whole, it continues to get better. So basically what patience does is it can avoid stopping or decay until the dev performance gets worse n times in a row or something like that. So, oh, sorry, this slide is out of order, but basically which optimizer do you want to use? So this is from the optimizer section. And basically, Atom is a good optimizer. It's usually fast, converge, and stable. But simple SGD tends to do very well in terms of generalization. And you should also basically always use learning rate decay. I found this to always be useful. So I think basically results are mixed. For example, in a paper that we wrote in 2017, we found Atom with learning rate decay generalized just as well as SGD, but there have been other contrary results here. So I think there's some degree of tuning or task specificity for each of these methods. Another thing that should definitely be in your toolkit is dropout. And neural nets have lots of parameters and are prone to overfitting, as I said before. What dropout does is it basically randomly zeroes out nodes in the hidden layer with a probability p, and it does this at training time only. So here's an example, like let's say you had 5 nodes in your hidden layer. You would zero out some of these nodes. And the reason why this is good is essentially it prevents the neural network from using individual parameters to strongly memorize a particular example, and rather requires them to learn more robust representations distributed across all of the nodes in the training data. And there are some nice interpretations of it that essentially demonstrate that this is similar to like training multiple models and ensembling to get them together. However, because the number of nodes at training and test time is different, scaling is necessary. Most neural network toolkits will do this for you already, but basically you can either scale the outputs by the probability, the dropout probability at test time, which is basically at test time, since you're not dropping things out, you reduce the scale of the outputs by the dropout probability to make them smaller. Or the other option, which is maybe more common, is to scale the outputs by 1 divided by 1 minus p at training time. And this will essentially adjust for the fact that you won't be using a dropout at test time at training time by upweighting the outputs. There are other alternatives as well. So there's something called drop connect. And what drop connect does is instead of zeroing out the individual nodes, you're zeroing out parameters in the neural network. And the advantage of this is if you want to use this together with some sort of optimized library that doesn't support dropout natively, you can just load your parameter matrix or vector or tensor or whatever and zero out the values in the parameter matrix. And you can do that and then use the parameter matrix downstream in any sort of neural network that you would like to be using. So we have a code example for this. You can take a look. It implements a lot of these optimization techniques or training techniques. So a final thing that would be good to talk about is operation batching. This is also absolutely essential to effectively training neural networks or efficiently training neural networks. So mini-batching, basically what it consists of is calculating multiple examples in a single pass through your neural network. So instead of calculating a single sentence, you would calculate multiple sentences. So the reason why this is good for efficiency in particular is that on modern hardware, 10 operations of size 1, so like let's say you wrote a for loop over a whole bunch of operations, is much slower than one operation of size 10. So like adding together 10 times 2 scalar values is much slower than adding together 2 vectors of size 10. And this is particularly true on kind of advanced acceleration hardware like GPUs or TPUs. So what mini-batching does is it combines together smaller operations into one big one. This also has training benefits as well. If you calculate the gradients of multiple examples before doing parameter updates, because as I mentioned before, if you calculate example by example, your gradients might kind of go all over the place every time you get a new example. But if you average together the gradients from lots of different examples, you'll stabilize the direction of the gradients and reduce its variance. So it's also very useful for training. So anyway, to give an idea of what this looks like computationally, let's say we had 3 affine transform and tanh operation combinations, where the input data, x1, x2, and x3 are different, but the parameter matrix and the bias vector are the same. So the way mini-batching would work is instead of doing these 3 operations individually, you would concatenate together all of your input data into a larger input matrix, do a single matrix multiplication instead of 3 different matrix multiplications, and then you would use an operation called broadcasting, which essentially implicitly duplicates this B along the columns, this vector B along the columns to get a matrix large B, which could then be added in here. And then you take the tanh over each of the elements. So this would be much, much faster than doing it the other way. So there's a couple ways you can do this. One way is manual mini-batching. So basically what you do is you group together similar operations and execute them all together. For example, in the case of a feed-forward language model, each word prediction in a sentence can be batched because for every word prediction, you are essentially feeding in the previous 2 words or previous n words, calculating representations and making a prediction. For other networks like recurrent neural networks or self-attention networks or things like this that we're going to be talking about later in the class, it's a little bit more complicated because essentially you need to group together sentences of different lengths, etc. So the shape of your network changes within a single mini batch. How this works depends on which toolkits you're using. So many toolkits, for example, like PyTorch, require you to add an extra dimension representing the batch size. They may have some convenience functions that will do things like load data or batch them together, etc. Other toolkits like Dynet or to a lesser degree TensorFlow have special mini batch operations that essentially allow you to kind of think in individual sentences, but then things get batched together for you automatically. So I have a code example here. Maybe I'll just go through it very briefly, but the basic idea is instead of inputting individual words and calculating loss functions over individual labels, you look up essentially a batch of words and you calculate the loss function over multiple output labels at the same time. So you calculate multiple examples at the same time. And we have a code example of this as well, if you'd like to take a look. So one exciting development in neural networks recently is that there are methods for automatically optimizing your computation. So for example, TensorFlow Fold and Dynet auto batching, essentially you build out the computation that you want to do, and then you press a button and it will go in and automatically batch together similar operations for you. So these are useful things to know about because especially for natural language processing, if you want to use kind of complicated structured networks like tree-based neural networks, etc. There's some overhead in doing this, but it's very convenient if you would like to use it for something like that. And so basically the way it works is for each mini batch and each data point in a mini batch, you define and add data, you sum the losses together, and then you call the forward algorithm where it automatically combines together mini batches of different sizes, et cetera, et cetera. And this is a figure from a paper where we talk about automatic mini batching, and basically it gives you very good improvements that come close to what you would get from manual batching without the extra effort of doing this. However, more recently, there's also been a trend for code level optimization. And basically what code level optimization does is it takes your program, for example, it takes a program in Python, and you write this program just normally, the easiest way that you can write it. For example, having a linear and an h and a tan h here, and then in some examples you can even have for loops, etc. But then within your code, you call this function here like torch.jit.trace. And what this does is this essentially does program analysis here and analyzes your code and optimizes it for you before you even start running your neural network. I think this is very exciting because it can basically go in and do batching beforehand and make your code more efficient. And for TorchScript, basically what this does is it converts it into, for example, efficient C++, kind of removing some of the overhead of Python. Another recent development that's interesting is the JAX neural network library, which also takes a similar approach and maybe has even more extensive program analysis tools, handling Python control flow structure, et cetera, et cetera. Okay, so now that I've talked a little bit about optimization, I'd like to talk about a case study. This is a slightly older case study, but one that's interesting nonetheless. It's a paper called Regularizing and Optimizing LSTM Language Models. Basically, it was a state-of-the-art method for recurrent neural network language modeling. And the reason why I think it's interesting and still worth reading, despite the fact that it's no longer representing the state-of-the-art, is it talks a lot about the different ways to optimize models. So it uses LSTMs, a variety of recurrent neural networks, as a backbone. You don't really need to know about them for the purpose of this class. But it applies a number of tricks to improve stability and prevent overfitting. So for example, it uses drop connect regularization. It uses SGD with averaging parameters, which is triggered when the model is close to convergence. It does dropout on recurrent connections in embeddings. It does weight tying, which we talked about before, where you have the input and output embedding vectors tied together. It also has independently tuned embedding and hidden layer sizes. So these are tuned in order to do as well as possible on a particular data set. And it also regularizes the activations of the networks. So it tries to make sure they don't get too large. And as I said, this was a strong baseline for language modeling, state of the art at the time. And one thing that's notable is it didn't change the model really at all. It used a standard LSTM model, but it just changed the training method. So this kind of shows exactly how much benefit you can get from adjusting training methods appropriately. Okay, so that's all I have for today. For the in-class discussion, I would like to discuss if you have experience with neural networks, what is your standard set of tricks that you use in most projects? And particularly if you've used neural networks that vary from genre to genre, some may be more useful in one area, such as vision, and some may be more useful in one area, such as NLP. What are they? Why do you think this is? Et cetera, et cetera. And in the discussion section, we'll probably have breakout rooms and try to separate into groups of people who have more experience or less experience with working with neural networks, so we can get a good mix there. So that is all I have for today, and I'm looking forward to seeing you in class.